In this video, I want to talk about one of the important tools that is available for astronomers to learn things about objects that are very, very far away, that all we can do is look at them. And that property of objects that we are interested in is the temperature. We talked about the fact that the electromagnetic spectrum extends from low energy to high energy, that the wavelength or the frequency of the light corresponds to the energy of that light. So low energy, low frequency, long wavelength at the radio end through visible ultraviolet X-rays to shorter and shorter wavelengths, higher and higher frequencies, and higher energies as you move up the electromagnetic spectrum. So for visible light, the lowest energy is red light, the highest energy is blue or violet light. We know that if you heat up an object, it causes it to glow. If I take a piece of metal and I put it in a furnace, it glows hotter and hotter and hotter. If you have an electric stove and you turn on the burners, they go from being essentially black or very dark gray to glowing red or orange. Incandescent light bulbs, which are hard to come by nowadays. Nowadays, most of our light bulbs are either compact fluorescent or LEDs, which don't give off light in this way. But old-fashioned incandescent light bulbs just made light by running electricity through some very, very thin wires until they got very, very hot. And that relationship between temperature and light is an important one, and it's one that we can actually exploit to learn things about objects that are glowing. It's also important to remember that it's not just hot objects that give off light. Everything gives off light, just not all light of a frequency or wavelength that we can see with our eyes. We are all probably very familiar in the COVID era of getting your temperature taken just by having somebody point something at your forehead. What is that thing they're pointing at your forehead? It is an infrared thermometer that is measuring the wavelength of electromagnetic radiation you are emitting as a body of 98.6 degrees, or if you have COVID, maybe 102, 103 degrees. And the relationship between the wavelength or frequency of that infrared light and your temperature is a mathematically precise relationship. You can get somebody to come to your house and take a picture of it with an infrared camera showing the places that are warmer, giving off more radiation. The windows are losing heat in this house, and find places where your house is poorly insulated because this infrared camera can see the infrared radiation being given off by the surfaces that make up your house. Physicists have an unusual word that we use to describe the light emitted by an object due to just its temperature. That word is blackbody radiation. And the meaning of that word, the place that that term comes from, is we're only interested in the radiation that a body is emitting, not any radiation that is reflecting. For example, my shirt that I'm wearing today is blue. It is not radiating blue light. It is reflecting blue light from the white lights that are shining on me here in my little makeshift studio. So we're not interested in the color of the object that it's reflecting to you. We're interested in the radiation that it is emitting due to its own temperature. So the perfect object to measure its radiation would be an object that's perfectly, utterly black, that reflects no radiation at all. We call that imaginary object a black body. So when we're talking about black body radiation, we're talking about just the light that an object is emitting due to its own temperature, not any light that it might be reflecting from its environment. Okay? So two things happen on an object when you heat it up. It gives off light. And it gives off more and more and more light the hotter and hotter and hotter it gets. But it also gives off light of a higher and higher and higher frequency the hotter and hotter it gets. And that relationship is actually a precise mathematical one. If you take an object that is glowing red hot, an object that is glowing with a yellow glow, and an object that is glowing white hot, those shapes of the curve of radiation that it gives off. And this is a graph of, for a particular object, for each wavelength of the electromagnetic spectrum, how much light does it give off of that wavelength. So the red object gives off red light and just a little bit of yellow light. The yellow object gives off a lot of yellow light, maybe even a little blue light, but most of what we see is yellow. An object that is white hot is giving off blue light and also yellow light and also red light. So our eyes see that as the color white, or maybe in the case of a very bright light, bluish white. These curves are called blackbody curves. There's a specific mathematical formula that I will not bore you with. It's very complicated. But the peak of each of these curves in wavelength or frequency corresponds to a particular temperature. So if we take the light from an object, spread it out into a rainbow, measure the intensity of those wavelengths, and find the peak, there is a one-to-one relationship between the location of that peak, the frequency or wavelength of light that is given off the most, and the temperature of that object. So a blackbody curve, measuring the blackbody curve, the blackbody radiation given off by an object, allows us to measure its temperature very, very easily. This is how we know what the temperatures of stars are. That's how we know that our sun has a surface temperature of around 6,000 degrees Kelvin, and that Betelgeuse, or red giant, is cooler because the light it gives off is redder. Its peak is more to the red. Its temperature is about 4,000 Kelvin on the surface. The Pleiades, a little tiny constellation, or it's not a constellation, it's a little grouping of stars that you can see in the winter in the constellation of Taurus, just to the right of Orion. It's sometimes called the Seven Sisters. It's a little kind of trapezoid-shaped group of stars. Some people can see 7 with the naked eye. Some people can see up to 11 with the naked eye. When you look at them through a telescope, you can see that they are blue. If you measure the light given off by those stars, the peak, the light that it gives off the most of, is in the blue. And mathematically, we can draw a one-to-one relationship between the location of that peak and the surface temperature of those stars, the temperature of the object giving off those bodies. So blackbody radiation, the peak wavelength or frequency of light given off by a hot radiating object, tells us its temperature. And this technique is not just good for visible light. We can use it for an infrared thermometer to measure your temperature by pointing at your forehead or pointing in your ear. We can build an ultraviolet telescope to measure the temperatures of things in the universe that are hotter than 10,000 degrees, whose peak is beyond the visible part of the spectrum into the ultraviolet. So this means that when you look in an astronomy book and it tells you the temperature of some star, or the temperature of the surface of the planet, and your question is, how do we know the temperature of the surface of this planet if we've never been there? How do we know the temperature of the cloud tops of Jupiter? This is how we know.